So Robert Cameron is a senior scientist here at the Max Planck Institute for Solar System Research. He's been here since 2003, and his research interests include solar physics, heliososmology, and dynamo theory. And today he will talk about the Babcock-Leighton solar dynamo. So thank you, Robert.
Okay, so I'm going to talk about the solar dynamo, and because I like observations, I'm giving the dates at the top in terms of Carrington rotation. So there's 27 days between is 1 unit, and so this is 30 years, and by now we have an extra solar cycle of this. And what the top panel is time and sine of the latitude, and this is the azimuthally averaged radial field at the solar surface. And the azimuthal average is made from the bottom images, which are put together maps of the solar magnetic field over the surface of the sun. And basically, the sun takes 1 Carrington rotation to rotate around the sun. And so every Carrington rotation, we can make a new map of the flux on the surface. And if you look at this map or this series of images, you'll see magnetic field popping out. This is popping out from below. And when it pops out from below, it does so in the forms of bipolar pairs, i.e. patches of positive and negative flux. If you look in the northern hemisphere, for example, you'll find that in one cycle, almost all the things which are popping up, the flux emergence, has the same east-west orientation. And what this tells us is that beneath the surface, there's a large scale, m is equal to 0, azimuthal magnetic field, which runs from east to west or west to east, and which flips from cycle to cycle. And this is known as Hale's law. The outline of this talk, since I'm discussing the dynamo, I'll talk first about the in-situ measurements, and then we'll follow the flux through remote sensing instruments, and looking at both the toroidal and toroidal flux budgets in 0D and 1D. So if we're talking about in-situ measurements, then we're not talking about measurements inside the sun, unfortunately. We're talking, in this case, about measurements more or less out at 1 AU, but some way around from the sun. And at this distance, the magnetic field coming from the sun is dominated by the Parker spiral. And because the sun is rotating, the whole magnetic configuration rotates around the axis. And because there's a solar wind carrying the material outwards, the field lines form spirals, and hence Parker's spiral. And fortunately, this is a rather easy geometric problem to solve. If you know how fast the sun is rotating and you know the speed of the wind, which you can measure using in-situ instruments, then you can determine the ratio between B phi and BR. You can also, of course, measure B phi and BR, and you can see how well this ratio is described by the Parker spiral. And if you do this, what you find is that although the Parker spiral is a dominant magnetic field, there's also a cyclically depending error. So there's a difference in the B phi you observe and the B phi you would expect from a pure Parker spiral. And this has something to do with the solar cycle, but it's not perfectly in phase. It happens a little bit earlier in terms of this error. And I'm not showing the units here, just where the zero line would be if there was no mistake at all. And this was work done by Bieber and Rust in 1995. To correct the proposed, so the reason for this excess flux is that purely toroidal field is also being carried out by the solar wind. So the solar wind consists of Parker's spiral, which is radial field, which is then just spiraling around the sun as it's forced out by the solar wind due to the sun's rotation, plus a component which is the loss of toroidal flux from the sun. And Bieber and Rust calculated from the measurements, from the in situ measurements, that about 5 times 10 to 23 Maxwell's of toroidal flux was being lost per hemisphere per cycle. This 5 times 10 to 23 is possibly not small, but let's see what we can compare it to. So we're going to follow the flux and see where this 5 times 10 to 23 Maxwell's comes from. And here the important point is it comes from the sun, and on the sun we see flux emerging. And after the emergence, the key observational result is that the magnetic field, after it's emerged, so a day or two after the emergence, moves around like corks. And this is what you'd expect from the induction equation if the field were purely vertical. So after emergence, the field at the surface is purely vertical. And it's purely vertical because magnetic pumping is removing any slant to the field below, radial pumping, and buoyancy above the surface keeps the tube vertical. So the tubes are radial at the surface, or the magnetic field is predominantly radial, the large-scale magnetic field, and moves around as if it were corks. And the induction equation, which we'll come to in a little bit, is what governs the evolution of the magnetic fields. And under the assumption that the field is purely radial at the surface, then the magnetic field moves the magnetic field according to the flows, and the important flows are the meridional flow, which carries stuff towards the pole, differential rotation, which the equator rotates at about 25 degrees, once every 25 days at the surface at the equator, and once every 36 days at the pole at the surface. The third velocity component is the convective motions, the granules, the supergranulation, which can effectively be treated as a diffusivity. You can put in these motions if you observe them or if you model them, but there's so many granules and their lifetime is so short compared with the timescales we're interested in that you can treat it as a random walk and therefore as a diffusivity. So in this case, it's rather, under those assumptions, it's rather easy to estimate the flux loss from the solar surface. Basically, if you have one emergence, boom, 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 so you have flux which was initially beneath the surface, and part of it pokes it up and goes through the surface, then the amount of flux lost initially is the flux in the tube times the distance over 2 pi times the solar radius. So the circumference of the sun at the particular latitude we're looking at, and the distance gives you the amount of the average flux which is removed. So it's interesting to note that most of the flux, or after emergence, most of the radial component of the flux is going to disappear. So if we look at a certain time, we have a radial flux coming up from the surface of the sun. In red, we have negative flux going back into the sun, and because of the solenoidality of the field, the amount of flux coming up gives us, according to the previous formula, the amount of, well, the flux in this segment will be equal to the flux which is coming up, which is equal to the flux going back down again. In time, because of the diffusion, these Gaussians will expand, and you should understand this as a random walk, and this is the expectation value. And you'll have a little bit of cancellation occurring at the bottom. Now, for the amount of toroidal field is unchanged. And you can consider this if you consider the picture before the top picture, so before we do the subtraction or the cancellation, and we can link, we compare all the points. So we compare the positive point and the negative point. And then you can imagine that this consists of a little Gaussian, or little delta function here, little delta function here, and the yellow one is another delta function, So now we have pairs of delta function. And we can, because the problem is translationally invariant, just push all these back together again, so all the delta functions are on top of one another. And then the bottom picture, and so because the choice of facts of this and this is the same, because the system is linear, we have that the choice of facts has not changed. And we can, of course, apply this much later in the system where the cancellation is now severe. So initially, their strength was 1.5 at this time, and now we've reduced the strength to 0.05, so reduction of a factor of 30. Almost all the horizontal flux or the radial flux has disappeared, but the toroidal flux stays the same because, again, we can make these pairs and rearrange everything because the problem is translationally invariant. And you can do this with equations, but this is the sort of physical or the graphical background. And so if you read the paper, we actually present the argument in terms of the equations, and we do it formally, but the graphical reasoning, it works. I think this tells it sort of better. And so this tells you, so even though all the radial flux has disappeared, the toroidal flux has stayed the same. So if we can estimate or if we can measure the toroidal flux at the time of emergence, then we have the time of, then we have the amount of toroidal flux lost for all other times. And as you move for flux loss per emergence, it's just phi LD over 2 pi. So this d over 2 pi r cos theta, cos lambda. This is because, so this is the fraction of this as against the whole circumference. And so if the tube went all the way around the whole circumference, this factor would be 1, and we would have lost all the flux contained in this segment. Otherwise, we only lose a fraction of the toroidal flux, but we need to sum this over all the emergences. Fortunately, we don't have to go out and measure it ourselves. Lots of observers have in the past done an extremely good job of measuring all these little emergences. For example, Hagner in 2001 measured the separation of bipolar pairs to be about 9 megameters on average. And if you consider the randomly orientation in terms of longitude and latitude, then the longitudinal separation on average is about 5.6 megameters. You can look at how much flux emerges per day. And again, Hagner 2001 gives a value of 1.25 times 10 to 23 Maxwells. Approximately 60% of these obey Hale's law, which means you need to multiply this number by 0.2, but 60% do, 40% don't, so 20% preferentially obey Hale's law. The emergences occur over the whole surface of the sun. These are ephemeral regions. This is just an observation. And so you can calculate the flux loss per day, and it's 5 times 10 to the 19 Maxwells per day per hemisphere. During minimum, or during maximum, it should be about twice this. And so you do the numbers, you multiply this by 365, and the factor of 2 because we're looking at maximum, and then you average with the minimum value. And in any case, you get to a cycle loss of 3 times 10 to 23 Maxwells per cycle per hemisphere. You can compare this to, or you can also calculate the loss from active regions using, and so these were the big regions which are 60 odd megameters, 100 megameters in the original movie I was shown. If you do this, however, you find the loss due to the active regions is smaller by about a factor of 10. But the total loss then is about 3.3 times 10 to 23 Maxwells per hemisphere per cycle. So again, 3.3 times 10 to 23 Maxwells per cycle per hemisphere from the observed from the remote sensing instruments looking at the surface of the sun and analyzed by lots of very patient people in the past. And this compares reasonably well with the Beaver and Astri salt of 5 times 10 to 23 Maxwell's of toroidal cycle rust per cycle. This was a 1 AU in situ measurement. So now the next question is, where does this value, this should be 10 to 23, never mind. Where does this value of 3 times 10 to 23 Maxwell's per hemisphere come from? So 3.3 or 5 times 10 to 23, somewhere in this range. Where's all that toroidal flux coming from? And to answer that question, I finally have to get to the induction equation. So this is the induction equation. It tells you the change in time of the magnetic field depends upon the velocity and the diffusivity. And it's a linear equation, provided u and of course eta are fixed. Whether or not it's linear, we can apply Stokes' theorem to this equation. And Stokes' theorem just tells you that the time derivative of the integral of b dot dA, where a is now some surface, and with respect to t is equal to some contour integral. And a here is any surface with a boundary delta a. Here we can actually make a little bit of some simplifications. The molecular diffusivity, this is incredibly small. So we can drop this term, and these terms we're going to actually make a little bit more complicated by splitting into an axisymmetric mean, so an azimuthal mean, for which I'll use these brackets, and small scale parts. So this is just u is equal to its axisymmetric mean plus some part which is not the axisymmetric mean. And if I want to look at the evolution of the axisymmetric component of the flux, then I only need to look at the axisymmetric flows and the axisymmetric contribution from the small scale flows. So because we're interested in the toroidal field in the net hemisphere, which we know we're losing at a rate of about 3 to 5 times 10 to 23 Maxwell's per cycle per hemisphere, we choose as our surface an equatorial plane in the northern hemisphere. We could have done it in the southern hemisphere if we were Australian, as I am, but in this case we did it in the northern hemisphere. And we choose our contour such that it goes along the surface of the photosphere where we can observe what's happening. It dips to the base of the convection zone along the equator, goes inside the solvent interior, and then comes back out of the axis. In the interior, we don't have to worry about the magnetic cycle. The magnetic cycle field does not penetrate significantly into the interior, so we don't need to worry about this component. We can move into a system rotating at the equatorial rate, at the rate of the equator, and then you'll see that near the equator, there's very, very little differential rotation. And so in this coordinate system, the large-scale flow is equal to 0 because we're now in a coordinate system rotating with the equator. And so if we integrate along here, we end up with nothing. If we integrate along here, we end up with nothing. And if we integrate along the equator, we also end up with nothing because whatever rotation system we're in do not have a singularity at the axis. The relevant components of u and b have to vanish. In particular, the u phi has to vanish. No azimuthal velocity along the axis. And so in this system, we have 0 from the large scale field here, we have 0 from the large scale field and flow here, and 0 here. And so we're left with only small scale contributions along the equator, small scale contributions along the axis and large and small scale contributions along the photosphere. The contributions from the small scale at the axis and the equator, by symmetry arguments, we can treat as a diffusivity. These symmetry arguments are basically the effect of the Coriolis force doesn't create toroidal field exactly at the axis or exactly at the equator. Things are different along the photosphere. So along the photosphere, we left the large scale flow and field contribute, and the contribution is given by the surface radial field times the surface differential rotation in the frame where the rotation at the equator, where we're rotating with the equatorial rate. And so you end up with an integral along the photosphere of the differential rotation times BR. And this is eminently observable. So this is BR at the surface. We've observed it, I showed you before. And we also observe the differential rotation at the surface. We can always do that in certainly in a frame which has zero velocity at the equator. And so you multiply this by this, and this is the integrand. You'll notice the integrand is completely dominated by the polar fields. And this is actually why the polar fields are a good predictor from cycle to cycle. But I'm not interested in prediction. I'm interested in how much we generate. So I can take this integral. I can actually integrate this. And if I integrate this, I find 5 to 8 times 10 to 23 Maxwells per cycle per hemisphere. We also had, from before, a loss term of 3 to 5 times 10 to 23 Maxwells per cycle per hemisphere. That was discussed in this later paper. And so basically the point is we're generating, by the winding up of the differential rotation, 5 to 8 times 10 to 23 Maxwells. And we're losing 3.3 to 5 times 10 to 23 Maxwells escaping through the solar surface. So we've seen at 1 AU, we're losing flux. We're seeing at surface, we're losing flux. And we see that we're generating a similar amount of flux by the only means possible for generating short of flux because of the Stokes theorem applied to the induction equation. So the conclusion is the source term for the toroidal flux is the toroidal flux near the poles being wound up by differential rotation, and the loss is mainly, but not entirely, flux emergence for the surface. We also lose a little bit of flux across the equator and the axis. A little bit of the toroidal flux cancels with what comes from the next cycle. This rate of that we're generating, that we're losing most of what we're seeing through flux emergence gives you a time scale for the flux emergence process of 12 to about 16 years. And this comes just from taking 5 and I have a 3. So our total flux produced per cycle is 5, and we lose somewhere between 3.3 and 5 per cycle. Therefore, the time scale for flux loss is somewhere between 12 and 16 years. To compare this with what you might think is coming from diffusion alone, well, the convection zone has a depth of about 200 megameters. Turbulent viscosity is about turbulent diffusivity is about 100 kilometers squared per second. And this gives you about 12 years if it were purely diffusion from the bottom of the convection zone. So at least part of this rate may be related to turbulent diffusion. So now we want to know, so now we know where the toroidal flux is coming from and where it's going from, but the toroidal flux is basically being generated by the winding up of these polar fields. And so the next question is, where do these polar fields come from? And the answer we again get from applying Stokes theorem. In this case, however, we're going to apply Stokes theorem to the surface of the photosphere in the northern hemisphere, and our contour will be the equator at the solar surface. And this was work done, for example, by Christo and in 2004, and we looked at implications based upon the observations, in particular the importance of the this term, the URB feeder in 2013. In any case, we apply Stokes theorem and we get this equation. So we've got two terms because the large scale flows zero at the equator at the surface. We only have two terms, and these are small scale contributions. So they'll be like turbulent diffusivity or flux emergence. So the first term actually is a turbulent diffusion. And it's if you look at the BR at the surface, what you find, so this is a map of the magnetic radial field at the surface, slightly different, lower resolution than the previous one I showed, but the details are the same. You'll find one polarity sits closer to the equator than the other polarity. And if we go back to the original image of I should have had a movie there. If we go back here, it corresponds, it's because when they emerge, these active regions, for reasons we don't completely understand, are somewhat tilted. They're tilted so that the trailing polarity is slightly closer to the pole and the leading polarity is slightly closer to the equator. And when you average over enough of those flux emergences, you find that one polarity is slightly closer to the equator than the other. In this case, the red polarity, the negative polarity for this cycle, is slightly closer. And so a little bit more of it can diffuse across the equator. And on the other hemisphere, the blue, so the blue diffuses across the equator. And at the end of the cycle, this all ends up in the poles. And yeah, so the question of where the polar fields come from, which is what's critical, all relies on getting stuff across the equator. And getting stuff across the equator relies on Joy's law, which is this tendency of the leading polarity to be slightly closer to the equator than the trailing polarity. But we know the diffusivity because we can actually watch the motion of the little quarks as they sit on the solar surface or the magnetic field at the surface. We watch it all day, we watch it all week. People watch it for 40 odd years, and you can tell it very reasonably obeys a diffusion type equation. And so this is actually a diffusing process. There's another contribution, which is coming from emergences not near the poles, but actually across the equator. So here we see an example in the red circle, and here we see July, August, September. These are separated by 27 days. And in the first one, there's only a hint of something, which is east-west aligned, and then something which is north-south aligned begins to emerge. And this north-south aligned feature, of course, is extremely efficient at putting positive flux in one hemisphere and negative flux in the other hemisphere, because it doesn't require diffusion. It relies directly on radial velocity carrying the feeder component of the field across the solar surface. And because the diffusivity is so weak, events like this, although extremely rare, play an extremely important role. And so far as we can tell, these events are no different from the events, the emergences at higher latitude, except it takes place over the equator. And if you look at the emergences wherever they occur, you find occasionally they're highly tilted. Occasionally they're highly tilted in positive, negative, and occasionally negative, positive. There's a large random component to the tilt, and this ends up being reflected in the statistics for these events. So this is just randomly, one has emerged with an extremely large tilt angle. If you put, if you look at, and because people have looked at all the emergences, made catalogs, including of the tilt angle, and if you put these into a model, you find the model very nicely, as it must, because Stokes' theorem and the induction equation will be in question. We very nicely reproduce the amount of flux which is being transported across the equator. And because at the end of the cycle, all the flux which is transported across the equator ends up at the pole, we now understand quantitatively where this polar field is coming from. It's coming from flux which is being transported across the equator. We know this from Stokes' theorem applied to the induction equation, and we know it's dominated by a systematic component coming from the Joyce law and the turbulent diffusion, but there's also a strong random component because the emergences are affected by convection, and the tilt angle varies by very, very strongly. If you put all the observations in, the model reproduces the changes in the total field we see. However, even if you look at this, you can see that it's not a simple smooth curve. The random noise is playing a big impact. And so we did this. Jay has done it, for example, at the MPS, but other groups such as Whitbread et al. Have also reproduced basic observation. So now we have Joyce law, and this is the tendency of the leading polarity to emerge closer to the equator as the cause of the systematic component of the toroidal field regeneration. And Joyce law itself is coming from the Coriolis force, but as I said, we don't know yet the exact cause of, and in particular, what flows the Coriolis force is acting on. Is Coriolis force acting on the flows associated with the buoyant rise of the tube, or with the convective flows, or more probably with some mixture between those two? And so this is a topic which is very interesting for current investigations. So this leads to the zero-dimensional sort of Babcock-Leighton, if you want, model of the solar cycle. The point is, toroidal field is generated by the winding up. So in the northern hemisphere, we take the radial field, the differential of the rotation, multiplies these together. This geometrical factor, and we're looking at the, okay, in this case, we're looking at the southern hemisphere. This is because I'm Australian. And if you take this, you multiply by this, you multiply by this, and you do the integral, you find out the amount of toroidal flux which is being generated, Stokes' theorem, and this is about 0.5 to minus 0.5 to plus 0.5 times 10 to 23 maximals per year. You get the correct value if you integrate over a cycle. And if you look at the loss, well, the loss term is flux emergence, so you have the amount of toroidal flux at the surface, which we can observe. You have the emergence velocity, which people have measured because it's the type of thing observers like to do. And you'll find out that the toroidal flux loss due to flux emergence is about 0.4 negative to 0.4 positive times 10 to 23 maxwells. So we've got a nice little cycle going on here where we generate toroidal flux and we lose it. In the same way, we have a nice little cycle where we generate toroidal field, toroidal field by flux emergence, which is tilted, and the tilt is captured here. It has to occur close to the equator because the whole story is about getting flux across the equator. And you can determine all these from observations extremely well. And this generates toroidal flux of about 10 to 22 maxwells per year. And the total flux which builds up. In this case, we don't have a loss mechanism because the only term which you have is the equator. Instead of a loss mechanism, the field just builds up, and then the new field of the opposite sign comes, replaces it, and then builds up itself. So we find toroidal fluxes at the poles, in this case the south pole, because I'm Australian, of about 10 to 22 maxwells. But if Aaron Birch were to have done this, since he's from the northern hemisphere, he would have chosen the northern hemisphere, but found the same values. So now I want to move on to the 1D representation of this problem. In the 1D problem, we have to make a few assumptions. So based upon the observations from Jasper, we're going to assume the the differential rotation is constant as a function of radius, except in this finished surface shear layer, and when assuming everything's restricted to within the convection zone. So again, we'll take the induction equation, which we now write out in its component pieces. And the thing we're going to do is we're going to integrate. We're going to integrate from the base of the convection zone to the solar surface. And we're going to, in particular, integrate the toroidal component of the field, so the phi component of the field. This is, of course, still the axisymmetric B phi. And this will give us the phi component of the field. And for the radial component of the field, we're just going to look at the surface magnetic field, but we're going to do it in terms of the vector potential A. Actually, we do it in terms of the phi component of the vector potential A. In any case, we then can take this formula, this definition of little b phi comma t, so the radial integral of the toroidal field, and we substitute this into the top formula, and we end up with a whole bunch of terms. We can simplify, and without just by mathematical definitions, and we end up with this equation here. And this equation gives us the time evolution of the toroidal field. We've introduced a V feeder, which is the return flow of the meridional circulation near or somewhere beneath the solar surface. And it's an average of the actual flow over the radius where the magnetic field is stored. And we've had to assume in doing this that the turbulent diffusivity has a particular functional form, but the change here is only on a factor of 2 for the eta. So these are both, I think, reasonable approximations. And when you do this, what you find is that we know the differential rotation. Oops. We know the differential rotation. We know the surface field. We can observe it, for example. And we know this tau. This is 12 to 16 years we discussed earlier. Eta 0 we can take from simulations of turbulent convection. And this V0 we also can measure, although I measured it last year. We can also look at the equation for the other component of the field. It's A, which is the radial component of the field, the vector potential at the surface. And if you do this, you find after a little bit of maths, you get this nice simple formula. And so this is the 1D Babcock-Leighton model. It has an equation for the subsurface toroidal field. It's an equation for the field at the surface. It has a relationship for the source term. And this is the term which connects the two equations. In particular, it's the source term for the toroidal field, and which tells you Joy's law takes field or produces toroidal field from flux emergence. The model works very well. So these are the observations of the toroidal field, the toroidal field, and the saturated toroidal field, just to show you that there is stuff up at high latitudes. This is the model eigenfunctions. You can solve it as an eigenfunction problem, and you find it matches very, very nicely. Again, although we have all these parameters, all of them, except for the alpha, this n is equal to 1, have been observed, or we're not sensitive to. For example, this epsilon parameter tells you the importance of the near surface shear layer, and it turns out the near surface shear layer is never very important in this type of model, just because there's not enough shear. All the others are observed, and the only free parameter you have is this alpha. And you choose the alpha according to Van Sadis et al. Their observation is that the sun is near a critical point where the dynamo action is close to switching off, and you use this to choose alpha. So I just want to point out that the meridional flow enters via this average, and it's usually an average over the lower half of the convection zone where the toroidal field is thought to be stored. And so a weak or small cancer cell, as was suggested by Professor Kosovachev a few talks ago, is essentially irrelevant from the point of view of a Babcock-Leighton type dynamo. So again, the model does fairly well if we look at the last 40 years. If we go back further, all we have are the sunspot numbers. Well, this is amazing we have, but we can essentially go back 10,000 years. The green here is the actual sunspot numbers, which we have for about 400 years. The blue is sunspot numbers reconstructed from cosmogenic isotopes. If you put in the alpha slightly above the critical value, some type of nonlinearity, and it turns out we're completely insensitive to nonlinearity, then you find the red curve is the mean from 1,000 realizations, and the pink is what you get from or the 25 to 75% model quartiles. So you find a quarter of the time it's outside of the pink, or half the time it's outside the pink. So the statistics of the green and the blue curves is actually quite good. The model doesn't work particularly well on the short terms where there's more noise than this model gets you. Because so this was the 1D model. I'm now going to quickly switch to the 0D model, back to the 0D model, and we can do this because if we're only slightly above the critical value for the onset of the dynamo to form, then, and we know the form of the dynamo in this type of situation is a Hopf bifurcation, then we consider the behavior as being governed by a Hopf bifurcation with noise. So we have the equation for the Hopf bifurcation, which is the normal form for this type of behavior, and we add some white noise, white multiplicative noise, and this is the same picture. It's before. The blue and the green are the observations, and the black is the model, and the gray are the 25% 5% model quartiles. And this brings us back to the 0D model we began with, and what we see is these limit cycles which come out of the observations. Time is essentially described by limit cycles plus noise. It's a multiplicative dynamo type noise, and it matches this study too. So here are my conclusions. Toroidal flux loss measured at 1 AU, 5 times 10 to 23. Toroidal flux at the solar surface, 3.3 times 10 to 23. Toroidal flux generation Stokes film, 5 to 8 times 10 to 23. These two top numbers, if they're out by a factor of 50%, it's not hideously surprising. There were estimates. To do all this, you require polar fluxes of about 10 to 22 Maxwells. At solar minimum, all the flux is in the polar caps. Toroidal flux needs to be taken across the equator in order to change the net flux in each hemisphere. This comes from Stokes theorem. There's two components. Oops. There's two components: a systematic component, which is coming from Joy's law, flux emergence, and some diffuse, turbulent, convective, diffusive motions, and a noise component, which is coming from the scatter and Joy's law. You can measure the scatter. It's been done in depth, and we observe just the right amount of scatter to explain the variations in the solar cycle we see from solar cycle to solar cycle. The 1D Babcock-Leighton model, the parameters, and there's a few, but they're all tightly constrained by observations, and it reproduces observations on timescales from years, thousands of years, 10,000 years. The model makes predictions of the next cycle, and this is actually the main, the strength of the polar field. It's the main way of predicting the next cycle. And the 0D model reproduces the observations on timescales longer than the cycle. And critical, but not discussed in this talk, is we really need to understand the flows, where they're coming from, and what's driving them. So I'm just going to finish by saying, why is the solar dynamo Babcock-Leighton dynamo? So I think I've tried to argue it is from observations very strongly. And the reason it turns out why this, I think, is the preferred solution is if you look at the velocity field, then it's basically featureless. This is more or less a desert. All we have is essentially latitudinal radial differential rotation. The dynamo is operating near the onset of dynamo action. The boundary condition is that the field is vertical at the surface. This is coming from buoyancy and pumping. Therefore, if we were to consider this type of boundary condition, we can consider it as half of a box, which is purely symmetric. And the solution you're going to have in such a box near onset, when the velocity field is featureless, is going to be the largest scale mode you can put in the box, which turns out to be the Babcock-Leighton mode. And so I will finish there with questions.